Hi, this is the third lesson and final lesson in the topic of static electricity. And in this lesson, we're going to talk about and learn about electric fields. Now, in the last two lessons, we dealt with these two situations. The first was used to illustrate the concept of static charge. And the second showed a potential application and use of static electricity. Now, both of these situations, both the jumper and the spray paint, are based on the fact that charged particles behave in certain ways when in the presence of other charged particles. Those could be oppositely charged particles or similarly charged particles. We saw that charged particles will exert forces of attraction and repulsion on each other, and this is dependent on the electric field. All charged particles, all the charged particles you see here, have an electric field. And an electric field is a region around a charged particle or an object within which a force could be exerted on other charged particles. Let's take a look and see what this means. When considering electric fields, we'll consider point charges. That's the electric field around a single point, just like this, as well as the charge around a plate. Now, a positively charged particle will have an electric field like this. And a negatively charged particle will have an electric field that looks like this. What do you notice about the direction of these arrows? When drawing and analyzing a charged particle's electric field, we can see that they are moving away from the positively charged particle, and they're also moving towards the negatively charged particle. Now, if we go back and recall what we learnt in lesson 1, this is exactly how a positively charged particle would behave. Two positively charged particles, so if we had a positively charged particle near another positively charged particle, they would repel and move away from each other. This would be repulsion. And when in the presence of a negatively charged particle, a positively charged particle will be attracted. This would be a force of attraction. So the rule is electric field lines are drawn showing the path a positively charged ion would move in an electric field, or a positively charged particle would move in an electric field. Now, if we have two charged particles together, like this, and they're oppositely charged, positively and negatively, a positive particle and a negative particle, what do you think these field lines are going to look like? Pause the video and think. So, we know that oppositely charged particles will attract. So, these lines will actually connect, like so. And here we have a force of attraction. On the other hand, when 2 point charges of the same charge are both positive in this case, how do you think they're going to behave? Pause the video and think. In this case, because these are the same charge, the same type of charge, we are going to have repulsion, and these field lines are going to move away from each other, like so. That's repulsion. Now, the next type of electric field we have to consider is the electric field between two parallel plates. Now, we can see that these two lines are in fact parallel. One's charged positively and the other charged negatively. What do you think these field lines will look like? Pause the video and have a go. So in this case, the lines will move directly from the positive to negative, just like we saw with the point charge example. This is known as a uniform electric field. As these lines are uniform and uniformly spaced, we have the same strength of electric field everywhere. What would a stronger electric field look like? Pause the video and have a go. So a stronger electric field would simply look like this, with far more lines present with far more lines present between these two plates. We have a greater density of lines and we have a stronger electric field. These lines are clearly much closer together. On the flip side of the coin, what would a weaker electric field look like? Pause the video and have a go. So a weaker electric field simply has fewer lines, and these lines are far more spaced out. They're far further apart. This represents a much weaker electric field. Now, a very common exam question is to consider how a proton, neutron, and electron move through an electric field like this. So here we have a positively charged particle, which could be a proton, moving through this electric field. How do you think it's going to behave? Pause the video and have a go. So, as we know, protons are positively charged. And if we go back to our first lesson, we would know that positive and positive will repel, and positive and negative attract. So the proton will be repelled by this top plate and attracted to the bottom plate. It's going to move in this direction, the direction of the electric field lines. So our proton is going to move like that. What about an electron, a negatively charged particle? Now an electron will be attracted to the positively charged plate and repelled by the negatively charged plate. So it's actually going to behave like this. It's going to move in the opposite direction of the proton. Now we can actually see that the electron traveled further than the proton. Whilst we're going through this, why do you think that is? And finally, a neutron. We know that neutrons do not have a charge. They're neutral. They're neither positive nor negative. So a neutron would not be attracted to this plate, nor repelled, and it would also not be attracted to this plate, nor repelled. So the neutron will simply pass straight through, like so. Going back to what we discussed earlier, as the proton is far heavier than the electron, it doesn't travel as far, and it ends up here on the negatively charged plate. But the electron travels far further and ends up on the positively charged plate. Feel free to go over this again if you haven't understood the first time. Next, we have one final question. Which positive charge, you can see we have two positive charges, is least affected by the negative charge, and why? Pause the video and think. So here we have two positive charges and one negative charge. The only difference between these two positive charges is that one is far closer to the negative charge and one is much further away. Which one do you think would be least effective? It's actually this one here. And that's because the electric field strength decreases as distance increases. So, as this is a greater distance, the electric field is weaker. The electric field strength decreases, and as a result, the force of attraction between the positive charge and the negative charge decreases with this distance. So as a result, the charges will be most affected at closer distances. It's really important to note. This decreases the attraction force. And that's it. I hope you found this lesson useful. If you have any questions, please do ask.